Hello everybody. So I was reading earlier in the Express newspaper about this exciting new discovery concerning black holes made by Xavier Calmet and his PhD student Folkert Kuipers. And this new discovery is very interesting because it builds on the work of Stephen Hawking. Stephen Hawking's major discovery about Hawking radiation, that black holes previously thought to be inert objects formed by dying stars, they actually radiate out thermal radiation. Which was quite a big new discovery about black holes back in the 1970s. What Calmet and Kuipers managed to have done is realise that as the black hole radiates away, it also loses pressure in the process. So it not only radiates thermal radiation, it also loses pressure as it radiates away, which really ought to come as no surprise, really, I don't think. I think that fits quite well with the general trends in astrophysics, or when considering the general trends associated with astrophysical bodies. For instance, stars lose pressure as they radiate away, do they not? And, various... Well, all objects in the universe, when they radiate away, lose pressure, of course. And I think what I'd like to pick up on from a sort of quantum gravity perspective on this is this notion of what sort of particle could be responsible for causing this loss of pressure, and the sort of hidden narrative behind all this so far as it concerns Hawking radiation. So, what would really be going on here in terms of quantum mechanics and gravity? So I think you have to think very much about particles tunneling inside and out from within the event horizon to outside the event horizon. And the particle I'm thinking of, if you're at all familiar with my own theory of quantum gravity, is of course the electron. And the electron would be picking up photons from within the black hole and transporting them via quantum tunneling outside the black hole and depositing them into space, which isn't quite the model that Stephen Hawking came up with. And I believe that in terms of a loss of pressure, this finding would be very much corroborated by the work of Calmet and Kuipers. So it would be a very important thing, I think, for me to try and get in touch with one of them at least. And go through the rigmarole of what I've been through before, trying to contact physics professors to get them interested in my ideas about quantum gravity. But I will shoot one of them at least an email, maybe both of them, I don't know, and try and sort of get a discussion going about quantum gravity. It'd be interesting to film it, actually. I think I might try and do that. I've probably got the time on my hands to do it. I've got the equipment. It might be worth doing. But so since it's not just virtual particles escaping back into space, and I won't really get into what a virtual particle is right now, since the black hole is losing pressure, it would have to be a real particle being emitted by the black hole back into space. And I suspect that those real particles are photons, more than likely gamma ray photons, being picked up from within the event horizon by a tunneling gravitational electron, if you like that sort of term, and then back into space, being emitted by the electron as Hawking radiation. And that's what would be going on there in terms of the quantum mechanics of, gravity associated with black holes. And I suppose also that model of Hawking radiation could also be adapted to any object, really, any object that's made of atoms, or any object made of atom-like structures, or any objects exhibiting a fermionic nature, i.e. made of fermions like quarks and electrons, for instance, or leptons, I should say. Not anything made of neutrinos, though. That would be the exception. Neutrinos would be sort of the exception to this rule, since they wouldn't be surrounded by electrons. Electrons wouldn't orbit a neutrino. but they would exchange particles with neutrinos. They would exchange probably Z particles with neutrinos and cause neutrino flavor oscillations, I suspect. But that's a topic for a different video, and it's something I haven't thought nearly hard enough about. So, yeah, it'd be very interesting to discuss physics with Xavier Calmet and his PhD student, Folkert Kuipers. And yeah, I should congratulate them on their discovery. Well, sort of, I should congratulate, well, like any big deal in physics or something, I don't know. Yeah, no, it'd be nice to try and, yeah, get a collaborative discussion going on camera, I reckon. I think it'd be really interesting to do that. Like a podcast, like a physics podcast. Actually, why haven't I thought about that before? I should have thought harder about this. I mean, I love physics, so it makes sense for me to try and get a physics podcast going. The wind tunnel is not a bad name for a physics podcast, let's face it. Physics is certainly involved in wind tunnels, albeit classical physics and fluid dynamics and everything like that. And yeah, I think it's quite a good idea. And it is a really great discovery, and it's something that lends a little crumb more of credibility to my idea, I think. So I'm quite pleased with that. It's a really, really good finding. So thank you everyone for watching. Bye bye bye. Love you lots, and I'll see you soon.